you to this lecture on QR factorization. This is a very popular factorization technique, and the utility of this method is it works even on rectangular matrices. So let's basically look into what exactly the QR factorization is all about and what are the conditions under the matrix in order to permit QR factorization. The QR decomposition method is a decomposition of the matrix into an orthogonal matrix and a triangular matrix. The QR decomposition of a real square matrix A is a decomposition of A as A is equal to Q into R. Q is an orthogonal matrix and R is an upper triangular matrix. Now the QR factorization will be unique when A is non-singular, and there are several methods for computing the QR decomposition. One very commonly used technique is the Gram-Schmidt process. So first let us visualize a QR. So the left-hand side matrix is a matrix A, and then the right-hand side is broken into Q and R. And you can observe the vectors of Q are written as E1, E2, E3, etc., which are nothing but unit vectors, and they should be mutually orthogonal. And then the right-hand side is an upper triangular matrix. So the matrix A, if it's sort of invertible, then the factorization represented as A is equal to Q over to R will be unique. And instead, if A is a complex square matrix, then A is equal to Q into R will have Q as a unitary matrix. Now we know that the unitary matrix is a complex analog of the real orthogonal matrix. Now let us basically see how to go about doing the QR factorization. This is a matrix with 4 rows and 3 columns. The first important thing to understand is that the columns of A should be linearly independent. Otherwise, there cannot be a QR factorization. So what we do is we transform these 3 column vectors, which at the moment are not orthogonal to each other, into 3 mutually orthogonal vectors. All of us know we can transform a basis of vectors which are not orthogonal into a new basis with orthogonal vectors using the Gram-Schmidt process. So let's see how it can be done. So let us start with U1 to be the first column of A, and U2 is the second column, U3 is the third column. Then we have to sort of transform these 3 into orthogonal vectors which are mutually perpendicular. So please revisit the lecture on Gram-Schmidt process, according to which we create 3 vectors v1, v2, v3, which are produced from u1, u2, and u3 with the special quality that they are mutually orthogonal. So if you take v1 as u1 and normalize it, we call it the vector e1. So e1 is equal to u1 divided by its norm. Of course, we have used the Euclidean norm here. Similarly, from u1 and u2, we can construct the vector v2 and then we normalize it and call it e2. Finally, using u1, u2, and u3, we can create the vector v3, which will be orthogonal not only to v1 but also to v2. And after finding that vector, we normalize that also. So I have not gone into the details because you have already been told how to apply the Gram-Schmidt process. So E1, E2, and E3 are 3 new column vectors obtained from U1, U2, and U3 through the Gram-Schmidt orthogonalization process and then we have normalized them to become unit vectors. So with this, the matrix Q can be constructed with E1 in the first column, E2 in the second column, E3 in the third column. You can observe that the order of Q is the same as the order of A. Now, once Q is obtained, then the question comes how to extract R. So let us start with A is equal to QR. And we know Q transpose Q is equal to I, which was emphasized in the first lecture in this particular unit, that whenever we have any matrix with orthonormal vectors as columns, then Q transpose Q is equal to I. So pre-multiply A is equal to QR with Q transpose, and then you will find that Q transpose A is equal to R. So once you have Q with Q, R can be obtained by a simple operation Q transpose into A. So for this particular matrix, when you find out R, you can observe that we have got an upper triangular matrix. So the QR factorization of A is shown in the next line. So how will this be useful? That's a very, very important question. We'll discuss that particular aspect when we come to the last module of how to apply the QR factorization for solving the system of equations. The next example is a problem in which we have a system of linear equations, and we would like to find the QR decomposition of this. So first, you extract the coefficient matrix, the solution vector X, and the right-hand side column vector B. And as explained in the first example, you first test that the three columns of the matrix A are linearly independent, and then using the Gram-Schmidt process, transform them into three new vectors of unit length, which are mutually orthogonal, and then that produces the matrix Q. So once Q is available, then the solution vector, and after having obtained R also by the method explained earlier. So how do you get R? R is obtained using Q transpose into A. And once you get R, then the solution vector is given by R inverse into Q transpose into B. And that produces the solution vector 1, 1, 1. So we can use the QR factorization method to solve a system of equations, but whenever already unique solution exists, one may not only use the QR factorization technique. We have got other options like LU and QR under the conditions which are required by those methods, but QR is also a good option. But there is another main reason why we use QR factorization for system of equations. So that is when we have an overdetermined system that is more equation than the number of unknowns. And obviously in those conditions, LU and Cholesky will fail. Then QR is a very good option to solve such systems of equations. So we'll return back to this particular concept in the last module when we talk about approximate solutions of system of equations.